Uh, Thank you for the introduction. I'm Joshua Woods. I'm a fifth-year PhD candidate at the Plasmadynamics and Electric Propulsion Laboratory here at University of Michigan, where we specialize in what's called electric propulsion. And joining me is Leanne Su. She wants to say a quick
Hello.
word about herself.
Hi, I'm a third year here. I work on a different type of hall thrust or of thruster than Josh does, which is superior. But we'll talk about that in the slides, I think. Josh, are you sharing them? Oh, yeah.
Let me. Oops.
Okay. Sweet. All right. Oh, it's the presenter view thing.
Okay.
I
Oh,
will
still.
No, it's still bad.
Okay, sorry. Let me.
Do you want me to share it?
Okay, how about that?
No, it's the same.
Oh my gosh. Oh, okay. Okay, so do this, and how about that?
Yeah.
Okay,
Okay,
there we go.
now
How
we're
many
good.
engineers does it take to get PowerPoint working?
2. Okay. All right. This is what we said. We're PhD candidates. We're in this lab. Okay. You want to go to the next slide? So kind of an overview. PEPL has been around for a number of years at this point. We work on electric propulsion systems and particularly experimental studies of low temperature, partially magnetized plasmas. So we've been around for almost 20 years now, and we're one of the largest EP labs in the country. A number of PhDs have been graduated from this lab and or are in the process of trying to graduate. And we work with a lot of various industries and government agencies like NASA, Air Force, and other industry companies to kind of develop new technologies, test out different thrusters. And throughout PEPL's long career, we've contributed to a number of various like flight programs and hardware. And then you can see in this little picture from a couple years ago, it's our lab director, our 2 lab directors, Professor Benjamin Jorns and Dean Alec Gallimore, along with a number of grad students at the time. And this is in our big vacuum chamber. Next slide. Okay, so this is kind of what I was saying. There's a lot of people, in fact, we're a big lab. So our lab directors, Dean Gallimore and Professor Jorns. We have a couple of affiliated faculty who contribute to a lot of the discussions. Eric, our test engineer, who keeps the entire facility running. And then right now there are 12 of us as graduate students, just doing our best. So yeah. Next slide. Okay, so what is electric propulsion? EP is kind of the electric car of space is the kind of common analogy. So if you have, like a Hummer or something, that's kind of the same thing, or not the same thing, but you can think of that as kind of your chemical rocket, versus an electric car like a Prius has great fuel economy. And so that's kind of the idea with EP devices. Next slide. So the low gas mileage of electric propulsion, I don't know why electric propulsion is in quotes, but the low gas mileage of EP makes it a great technology for cheaper space exploration, because you can go up with a lot less fuel, which makes it a lot cheaper, or you can go up with the same amount of fuel and therefore go a lot further once you're in space. Next slide. So this is kind of, what we were saying. A chemical rocket will expel a large amount of propellant at a very slow speed. Whereas for EP, you have a small quantity of propellant at a very fast speed. And so what this means is that the specific impulse of EP devices is considerably higher than the specific impulse of chemical rockets, which kind of in turn means that the propellant mass for EP devices is much smaller than that of chemical rockets, which means if we wanted to get to the same place, like let's say Mars, then electric thrusters would be kind of the way to go because they require so much less propellant. Yeah, so this is just a visual comparison, I guess. You can see kind of what you would need sizing wise for a propellant tank on a traditional chemical system versus on an EP system. So the benefit of using EP means that we can not only have cheaper missions, but also access new mission spaces. And so these stacked payloads to geosynchronous orbit essentially lets us, have twice as much payload for the same cost that is launched into orbit. We can have crewed exploration through things like the Deep Space Gateway, and then deep space exploration like the Dawn mission, which lets us go, past the edges of the solar system, into and past the edges. And then there's also like mega constellations. So the Starlink satellite system that SpaceX launched and is still in the process of launching all runs on electric propulsion because it's so much more efficient to use that for in-space propulsion. So there's a lot of different types of EP systems. There's kind of a couple of different categories. So there's thermal expansion or thermoelectric. So chemical nozzles kind of fall into this regime, but there's also things like resistojets and arc jets, which are electrothermal nozzles, and magnetic nozzles. We have light pressure devices, which isn't something that our lab focuses on, but that uses things like solar sails or laser reflection. A lot of the devices in our lab are electrostatic and electromagnetic. So under electrostatic, we have gridded ion thrusters, Hall thrusters, and Electrospray. And we'll talk about all these in more detail later on. And in electromagnetic, we have magnetopulse dynamic thrusters, MPDs, as well as
magnetoplasmadynamic.
Yeah, thank you. As well as a number of other thrusters that Josh knows more about. So here's kind of an overview of some of the things that PEPL is currently very interested in. So if you look at the top left here, we have high power plasma propulsion. And so this includes the nested Hall thruster. So the X3 is a 100 kilowatt class nested Hall thruster that the University of Michigan helped develop. It's set a number of records for the highest thrust from a Hall thruster, as well as the highest operation power. And the whole idea of like this nested channel thing is as you scale to higher powers, you want to try to make the best use of that space that you can. So then when you go to a higher or a larger radius, then you kind of nest more channels inside so you can increase your thrust density. So you can kind of see how big these thrusters get with this little comparison to the football helmet. Another thing that PEPL investigates is the physics of Hall thruster operation. So Hall thrusters are a device that have been around for decades at this point, and they're all of the Starlink satellites run on Hall thrusters. They're a commonly used device, but the physics behind them are still really poorly understood. And so one thing that our lab looks into is investigating kind of some of the dynamics of Hall thrusters, which can then help us not only better understand the physics, but also help to improve performance in the future. This also includes like spacecraft interactions. One of the biggest challenges with EP testing is that when you have a vacuum chamber on the ground, it's never going to be the exact same as your orbital conditions. And so a lot of the work that we do kind of involves extrapolating the ground test data that we have to in-orbit performance. Plasma diagnostic development kind of ties into this. So we have a number of different diagnostics in the lab that we use to characterize performance. We have a thrust stand for performance measurements, a number of thrust stands actually now, and as well as far field diagnostic suites. So a number of different probes that help us characterize the plume of an electric propulsion device. And there's also various optical diagnostics like laser-induced fluorescence, which helps us identify the the ion velocity distributions, among other kind of more advanced laser diagnostics. And last of all, there's what are kind of called advanced concepts. So these are EP devices or types of electric propulsion that aren't as well established and maybe don't have as much flight heritage, but have really like a lot of promise for future use. So this includes field reversed configuration thrusters, magnetic nozzles, and a lot of micropropulsion concepts, including electrosprays, as well as microwave and helicon, however you pronounce it. Next slide. So kind of going back to one of those first topics was the on Hall thrusters. The H9 is one of kind of PEPL's premier test beds. It's a thruster that's shared between, or there's 4 identical copies of it, one here at Michigan, one at Georgia Tech, one at NASA, and one at AFRL. So having the exact same thruster lets us kind of make comparisons between performance without having to kind of take into account all the design differences. And so the H9 has a lot of the same design features that the Hermes system, which is the 12.5 kilowatt Hall thruster that NASA's working on. They're kind of in the same family. So one thing they have is something called magnetic shielding, where the field lines in the channel of the Hall thruster are shaped in a way that mitigates erosion. And so erosion used to be one of the biggest issues for Hall thrusters, but now that we have shielding, that's kind of extended the lifetimes by quite a bit, as well as, and some of the other commonalities are just in the design of the anode and in the materials used. And the H9 nominally is 3 to 9 kilowatt operation. A couple of additional things with Hall thruster research specifically, we're looking at alternate propellants and materials and kind of design concepts. So xenon is the propellant most typically used for Hall thruster operation because it has the highest mass for, it gives us the highest thrust to power essentially. But xenon is really expensive and it's kind of difficult to procure. And so one of the alternatives that we're looking at is krypton. And you can see it's like this purple color instead of the blue that you saw on the last slide, which is what xenon is. We're also looking at graphite chambers. So you can see in this picture with the white below with the white channels, those are made of a ceramic called boron nitride, and they're extremely fragile and extremely difficult to machine. And so replacing them with a material that's more robust would definitely help with the ease of testing and running these types of thrusters. And then nested channels, as we talked about before. One thing that we're trying to achieve is high current density operation. And so as we look at Hall thrusters and other types of EP devices for deep space missions, it becomes more and more important to be able to get to these high power regimes. And then kind of things I talked about before, facility effects. So how do we get the data that we have from here on the ground and then extrapolate that to in-space operation, and then some of the things behind the physics. So one interesting thing is the breathing mode. So you can see in this little GIF here how the Hall thruster kind of looks like it's breathing. It has like this pulsing phenomenon. And so that's something that's not well understood. So a number of people in our lab have or are currently working on this problem, as well as trying to understand electron dynamics within the Hall thruster.
Okay, so I'll jump in here now because even though Hall thrusters are what we would consider the state-of-the-art sort of classical systems being used in EP and really widely being explored across the numerous institutions, there are a number of other alternative concepts for electric propulsion that fill different niches. So the one that I research is what's called a rotating magnetic field thruster, as opposed to a Hall thruster, which establishes a steady electric field to accelerate its ions to produce thrust. The RMF thruster is a type of inductive pulse plasma thruster, which means that it couples its energy not through electrostatic fields, but by time varying magnetic fields. So this causes it to be inductive in nature, and it's pulsed so that instead of constantly flowing your ion stream, you're actually charging up usually these giant capacitors and then discharging them very quickly, and then you're pulsing that at a couple hundred hertz to a kilohertz that you've achieved steady thrust. It's a great alternate high power solution, and currently our RMF thruster is able to operate up to 4 kilowatts, but the technology in general aims to go beyond the 100 kilowatt range to really achieve some higher power regimes comparable to the X3 Hall thruster. These thrusters are particularly suited for this because they don't suffer from theoretically the same current density scaling issues that Hall thrusters might experience. So you could just keep on upping the power without necessarily increasing the mass of the thruster. They're also propellant agnostic, which means that you can throw in, carbon dioxide, water, whatever. And since there's no plasma wetted electrodes, you won't have as much erosion. Current research projects are mainly focused on establishing some performance models and designing and optimizing these types of thrusters, along with further down the line, seeing how the plasma actually detaches from the magnetic field lines. Here's actually a high-speed video. So this is over the course of about 200 microseconds. The thruster is on the left and it's shooting out like a plasma ball towards the right at, a couple thousand meters per second, ideally. Oh, there you go. Another type of thruster is called the Electron cyclotron resonance thruster, which is a big fancy name for microwave thruster. Yes, all we do is we take microwaves just like you'd find in your microwave, and we use that to heat up plasma. These are great due to their simple design. They only need like one power supply as opposed to some of these other more complicated thrusters. They're an ideal solution for small sat propulsion. And so a lot of our research projects are going into investigating how these various microwaves are coupling to the plasma and how we can boost performance that way, as well as similar to the RMF thruster, looking at how the plasma detaches from those magnetic field lines. And of course, we have to have a video of this. It's a steady flow system, so it's not pulse. It's more like the Hall thruster, and that orange glow that you're seeing is like I think it's like some water or maybe some extra vapor kind of burning off initially once it starts. And then you see that more collimated bluish purple tint due to the xenon. And these are only about 100 watts, so pretty small. Okay, more YouTube recommendations. All right. And finally, we have probably the smallest, but also the most scalable thruster in our inventory, which is the Electrospray thruster. These operate completely differently. Well, it has much more unique operating principles than what's been shown previously, and that they use, instead of a plasma, they use an ionic fluid. And they have these very thin, a couple of microns in diameter emitters that form a Taylor cone, which is a Taylor cone instability at the tip of the emitters. And then you, at a certain distance away, you have a extractor electrode. And all that said, all that being said, what you end up getting are these very high efficiency, greater than 90%, but about 10 micronewtons thrust per emitter type thrusters that you can then take each one of these emitters and then put like thousands of them on a plate to scale up your thruster. So these are fairly new, although they have been flown before. And so our research is really investigating how can we better scale up these devices to get more thrust while retaining that nice efficiency that we typically get. And I'll kind of speed through these, but PEPL is renowned for its testing facilities. The crown jewel of our lab is the large vacuum test facility, which, very creative name. But it involves about 19 cryo pumps, which allows us to get to an operational vacuum of about 10 to the minus 8 torr, probably about 10 to the minus 6 to the minus 5. We're actually operating the thruster, which is really nice because we want to get as close to a vacuum environment to simulate space as possible. And it's a 6 meter by 9 meter chamber, so it's pretty large. Compare that to some of the other state-of-the-art facilities. Mainly, I like to we can kind of compare it to the NASA Glenn Research Facility, where it has a comparable, a bit on the lower side and compared to NASA's facility, but still up there as far as pumping speed goes. So this allows us to really operate some of these higher power, higher flow thrusters. In addition, we have several smaller chambers to test, like cathodes, which are key to operating Hall thrusters. This smaller chamber with great pumping speed we call Junior, which allows us to really get down to low pressures for our other small thrusters, and then dedicated thruster chambers for the ECR as well as the Electrospray. To test all these thrusters, we have an assortment of probing diagnostics, including near field and far field probes. And when I say near field, I just mean like right up close to the thruster, and far field is, several meters or thruster diameters away from the thruster. And I could spend all day going to how each of these diagnostics work, but essentially what it boils down to is we put a piece of conducting material, typically, a metal, and we put it into the plasma plume, and then we could do all sorts of stuff to it and extract tons of information about the temperature, the densities, all that about the plasma. So we can really get a wealth of information just from some simple conductors. But they can't interfere with the plasma dynamics. So if we can, we will use something like a laser-induced fluorescence, which is a non-invasive type of probing. And this in particular is really nice because even though it can be pretty complicated to explain and set up, what it allows us to do is directly measure how fast our ions are moving in the thruster and in the plume itself. Also, just to get some of those fantastic images, we have an assortment of high-speed imaging devices. That's where that video of the RMF thruster firing came from. And we also have a few thrust stands. The thrust stands allow us to directly measure the thrust of the thruster, which is ideal to know if you're testing these types of devices. But they're pretty sensitive and can be unwieldy just due to the fact that we're generating such low amounts of thrust. On a good day with a large thruster, we can generate up to a Newton, but typically it's not uncommon for us to generate only a few millinewtons of thrust. So these have to be very sensitive to pick those up. And there's a number of different factors that you have to consider when actually operating this stand. And finally, PEPL is an experimental lab first, but we also have a number of computational and modeling capabilities, including some of the standard stuff like COMSOL for electromagnetic modeling. But we also have access to more advanced thruster modeling that's made, for instance, in-house at NASA that allows us to model Hall thrusters and also Electrosprays. So with that, I'll open up for questions. Yep, this is a video. I think this is the X3.
No, it's the
H9
H9 running on Krypton, which it doesn't like.
This is what Leanne works on, so she throws it in there anytime she can.
Yeah, it's pretty.
Thank you both for coming to talk to us today. It's been really cool hearing all the different projects you guys get to work on, and you don't often hear of cleaner engines for space, because typically the flashier ones are chemical based, but it's nice to see that electrical propulsion is getting much more efficient and has a lot more uses than a lot of people may think. I do want to ask a question that was put in the chat. How can students in undergrad or who have no experience with this get involved with PEPL research?
Oh, so we actually have like a special undergrad outreach experimental program that Leanne is part of called Maze. If she wants to speak to that.
Yeah, so Maze is kind of, it's been intermittent the past few years because we kind of had to stop during COVID. But basically it's one of the older PEPL Hall thrusters, the PEPL 70, which is a low power Hall thruster. We have undergrads work on, and we have kind of a test demo chamber, like a small vacuum chamber that we can actually take to local high schools or science fairs and stuff like that to demo it. And so if you're interested in maze, you can, honestly, in addition to maze, actually, our PI, Professor Jorns, has a number, usually takes on undergrads for research projects, both undergrads and master's students, actually, for research projects, commonly in the summer, and sometimes also throughout the school year. And so what that entails is usually kind of helping one of the grad students with one of their projects, or, you know, getting assigned a project for lab maintenance, something like that. So yeah, so I would say you can just kind of cold email Professor Jorns, and ask if there's, you know, any available opportunities, or you could reach out to me, although I'll probably just end up redirecting you. But yeah.
Yeah, and actually, if you go on our website, on the university's website for us, if you just Google PEPL, it'll be like the first thing that pops up. But you can look through all of our research projects. You can see what students are working on what, and then our emails are listed there. So if you literally, you could just like shoot us an email like, oh, I'm interested in working on this. Here's my experience, and our advisor is pretty open to taking in undergrads.
Awesome, thank you.
I have a question. So first off, I just want to say thank you for coming and sharing all about PEPL. It's probably the coolest research, in my opinion, at Michigan. And I'm kind of, you know, coming out the door, but like, I always thought it was really cool. But I have kind of a fun question. So, what do you think that electric propulsion has application in human spaceflight in the future? Because I know there's a big trade-off between having a high efficiency propulsion, but also it takes a lot of time to get anywhere.
Yeah,
that's a.
You want to take it, or should I?
I could take it.
Okay.
That's a good question, because that's actually what got me into it. I actually interned down at Johnson Space Center down in Houston, which is like the human spaceflight branch of NASA. So I've always been interested in, you know, how can we get humans into space and, you know, further away from Earth. And so that's definitely one of the focuses of high power electric propulsion. That's why we're so interested in, for instance, like the higher power Hall thrusters, as well as the higher power inductive pulse thrusters, like the one I'm working on. We're not there yet because, well, you could take a lot of these smaller thrusters and just put like 100 of them on your spacecraft and see what happens, but that's not a very efficient way to go about it. Ideally, you want to really have a thruster with a high thrust density. So we need something like on the order of like, you know, a thruster that can be 100 kilowatts, you know, to a megawatt. And then maybe we could talk about like adding more, because it becomes a lot more scalable at that point to just start stacking these thrusters on your spacecraft. So we're not there yet, but that is the goal.
Right. Thank you.
Oh, sorry. The X3 actually was also selected for, there's been a number of mission studies essentially on, you know, kind of what that exact trade-off is. And one of the kind of settled upon potentially optimal kind of configurations is basically having a more powerful, like traditional chemical rocket to take humans to Mars, just to, you know, minimize the time that they spend under the radiation of space and everything. But to have actually cargo missions that are powered by EP. So the X3, that 100 kilowatt Hall thruster, was selected along with a number of other thrusters, including Vasimir, which is a pretty well-known one in Texas. And so these were selected as candidates for the cargo aspect of that mission specifically. So I think, you know, even if electric propulsion isn't necessarily on the ship with the human in it, I think it definitely is an enabling technology for human spaceflight in general.
Okay, yeah, that clarifies a lot. And like, aren't there spacecraft that have like a combination of the two, where like big transit, you're using chemical propulsion, but then for like, you know, small changes in your attitude, you use?
Yeah, absolutely. Yeah, you'll never be using, you know, you're never gonna spit out some xenon to get yourself out of the gravity well of Earth, because that would be very hard. But yeah, a lot of like satellites will have a couple of Hall thrusters on them. for orbit adjustments, but then they'll also have some heavy duty rockets for impulsive maneuvers.
All right. There's a question in the chat. I'll read that one first. So they're asking, what kind of step transformers do you design in lab, and what kind of coolant would you use? Oil-based or other types?
Kind of step transformers? We don't really design transformers ourselves. Well, actually, the inductive thrusters that we design we more or less do treat them like transformers, but I don't think, maybe I'm not the best person to answer, but I'm not sure if they're the transformers that you're referring to, or maybe I'm just trying to ballpark, spitball. But what was the second part of that question?
What type of coolant would you use?
Okay.
Maybe the same person that said that they might email, so that might be a good question.
Okay.
Addressing that eventually, but
yeah, so I can't speak to the cooling aspect because these thrusters can get pretty hot. So for something like a Hall thruster, typically we just allow it to radiatively cool throughout the chamber. But for the RMF thruster, we actually have coolant lines wrapped up, and it uses a mix of like water and glycol to help chill the thruster. Hasn't been too successful. It puts out a lot of heat because it's not very efficient yet. So we're getting power dumped into spots that we don't really want. But
the Hall thruster also struggles with temperature, and it doesn't have coolant. It's supposed to just, be able to radiate it away, but it's not very good at it all the time. So.
That's one of the biggest, actually, hurdles that you have to overcome when pumping up to higher power. Because if it's not being dumped to the plasma, it's being dumped somewhere.
Yeah, that's actually one of the material investigations, like looking at graphite. One of the reasons people like the idea of it, aside from, it doesn't break when you look at it funny the way that ceramics do, it's also just a lot better at like dissipating heat. And so hopefully, if we had thrusters with graphite instead of boron nitride, we could get to some of those higher temperatures without worrying about frying the whole thing.
Yeah. We can actually run the Hall thrusters for like hours on end, but the RMF thruster, we can only run it for about 5 minutes before like the power supply starts like, smoking.
The RMF folks are cowboying.
It's a fun. We're safe, but
But they have a fire extinguisher in case.
Yeah, that's good. I actually have a follow-up to that. So you mentioned it briefly during the RMF portion, but what is there like a difference, I guess, in the use cases for Hall thrusters versus RMFs? Or is it sort of just trying to figure out which one is the best general use case wise?
Yeah, so for all these thrusters, they sort of have their own regimes that they can really shine in. Right now, we're saying that Hall thrusters, like a lot of Hall thrusters operate in like a few kilowatts to, high hundreds of watts range. A lot of those magnetic nozzle thrusters operate, those in electrothermal, they're, a couple of 100 watts or whatever on small sats. But in particular, one of the attractive elements of the RMF thruster and other inductive, I want to like expand this out to like other inductive thrusters that use these changing magnetic fields to basically impart power from a distance. As opposed to like a Hall thruster or ion thruster, where your plasma might be actually hitting an electrode, so like a piece of your thruster, the inductive thrusters don't encounter that issue. So what that means is that you can use something called in-situ resource utilization technology, wherein you can use any sort of gases or other propellants that you can scoop up from whatever destination you go to. So for instance, on Mars, you can have your RMF thruster have a full tank, and then once it lands on Mars, it has an empty tank, but then you start scrubbing CO2 or water or whatever you can fit in your tank, and then you can just feed that into your thruster. It'll give you different performance characteristics, but you will get thrust out of that, and it'll be able to operate okay. Hall thrusters can do that to a limited extent, but you really start to get concerned about some of these more reactive gases as well as erosion on the thruster itself.
All right, thanks. There's another question in the chat, which I think we have time to take. So they're asking, can you share plasma photos from your experiments? Sorry. I think artists can do a great job with them. So I'm not, I don't, you can also feel free to raise your hand and we'll unmute you if you want to elaborate on that, but.
We actually have like a PEPL YouTube channel, which is relatively kind of became more active relatively recently. And so there's a lot of kind of cool videos there. The PEPL website honestly also has a lot of, like, we call them glamour shots, kind of the thrusters looking pretty before they, usually taken 10 seconds before they break. So yeah, there's plenty of photos out there if you're just kind of interested.
Having nice photos really helps when you're trying to convince people to give you money.
Yeah, that's our advisor always makes us take pretty pictures.
Like, see, it's real.
Look,
real.
it's working. Look how
Gets
pretty.
people excited, yeah.
Yeah, it gets people excited, yeah.
Yeah, I don't see any new questions. So
Awesome. Thank you both for coming to talk to us today. It was really great hearing from you and learning more about all this and how people can get involved.